Hello, everyone. Welcome to our fourth lecture in artificial intelligence. Um, in the previous lecture, we started looking at um, problem solving in artificial intelligence, where we introduced the concept of search, where we said when an intelligent agent is trying to solve a problem, it goes through the process of searching for a solution. Now, one thing that we talked about was how you formulate a problem or how you define a search problem in artificial intelligence. So what we said was when you're defining a search problem, you should indicate the following. One, you should indicate the state space. Now, the state space, we're talking about all the possible states that can be reached from an initial state. The initial state, we are talking about where the agent is currently. So, for a navigation problem, imagine I'm trying to use a navigator to move from Kitwe to Ndola or from Kitwe to Lusaka. So, the initial state is where the navigator currently is, and that is Kitwe. And then the state space, we're going to list all the states that can be reached from Kitwe by some sequence of actions. So from Kitwe, for example, if I head south, I'll get to Ndola. If I head north, or maybe let's say northwest, don't worry about the directions, but let's assume, let's say Chingola, Mufurila are in the northern part of Kitwe. So if I head in those directions, I will reach, I'll reach Chingola. So what we are saying is the state space, we are going to list all the states that can be reached. So in a navigation problem where we are looking at towns, for example, so the different towns that we can reach from Kitwe by some movement in a particular direction will be our state space. Then the set of possible actions, So in a navigation problem is the directions we can move. So we can say move north, move south, move east, move west. So those would be the possible actions that the agent will have. Then the transition model, where we said will describe the result of each action to say when we are in this state and a particular action is taken, this is what would happen. Then we talked about the action cost, that is the cost attached to each action. And then the goal test, that is how do we determine if a goal has been reached. So that is how we define a search problem. Now, I will talk about the state space and then move to how we reach how we reach or how we go about or how an agent will go about searching for a solution. So I'm going to use this. This illustration is a map of Romania. So assuming this is our map, just to help us with the conversation, um, if we imagine this map, there are different towns. Now remember what we said about the state space. The state space, we are going to show all the towns or all the states that can be reached from some initial state. So let's say the initial state is here, which is Arad. All the towns that can be reached from Arad by taking some steps will be part of our state space. So we are going to have our state space, and from this state space, the agent is going to go about searching whether we've reached the goal. So it will keep searching until it determines the path to get to a particular goal. So that's what we are trying to look at. So in this second part, we now want to talk about search strategies. We want to talk about search strategies. That is, how do we recognize a solution? Given we've defined the problem, now we want to look at how we are going to navigate through the state space to find a solution. So if we look at this idea, remember this is the same map that we were looking at. So the things that we do, uh, remember we said an agent will be in an initial state, and then we give it a task. Give me the direction or give me the path to get to Bucharest. So the agent will have to start checking. First of all, it knows that it's in Arad, so it will need to check. Am I in the go test, in the go state? No. Then, depending on the strategy that it will use, it will have to check. Okay. It checks the next town in the north, for example. Is this a go? No. Then it checks the next one. Is this the go? No. Then it checks. So after checking that these are not the go, then it will now have to look at maybe is the child to Zerint or is the next town after Zerint the go? Or it will check is the next town after Sibiu the go? So it will keep checking just like that. So here basically what we're saying is yeah, I've already mentioned the first check whether where you are is the goal. If not, then you keep checking. So you keep checking by applying some operators. Okay, now where we are starting from, or as we are carrying out with this search, we are going to form some search tree. Don't worry about these terms. As we go on, all this will become clearer as we look at the example. So this is where what we're trying to say. First step, you are in the initial state. So in the initial state, you check, you are in Arad. Is this a go? No. Then you now expand Arad. You consider the towns that are connected directly to Arad, one step from Arad. So which are Sibiu, this one, and Zerint. After this, you now look at the children. So these which are coming from Arad, we are going to call them maybe the children of Arad, where we're coming from. So next we'll look at Sibiu. Sibiu, when we are in Sibiu, where can we go? So if I can just go back. So here we are saying from Arad, I can reach this town, reach that town, reach that town. Now, if I go to Sibiu, then I can say, okay, from Sibiu, where can I go? Oh, okay, there's Odaria, there's Ferrara, there's this other town, and there's a possibility of going back. So Sibiu has 4 nodes coming from here. Okay, so we now check the children whether each one of these is a go. If not, we'll keep expanding until we get to the goal that we want to achieve. So basically, this is what is happening here. We are saying we start from here. If this is not a goal, then we look at the children. If none of the children is the goal, then we move to the children of the children. The children of the children until we get to the goal. Later on, I'm going to talk about how we can avoid having a loop where, for example, here we started from Arad. We know that it's not a goal, but when we get to Sibiu, there is a possibility of going back to Sibiu, to Arad, sorry. Since we already know that this is not a goal, we can do something about it so that we avoid having a loop where we keep going back and forth between states which we know are not the goal. Okay, so I now want to introduce the concept of a search tree. So now let me use this simplified diagram. So with our diagram, let's say we want to expand. So we are here. So we have our state A there as the starting point. Now, from here, we check, is this the goal? No, the goal we are looking at is this one. So we say, okay, let's now consider the children. So the children are B and C. Okay, so this is B and C. Okay, then we go to B, we check, is B the goal? No. So we now look at who are the children of B. So the children of B are, so from when I say the children of B, we are saying when we are in a particular state, where else can we go? So from B, we can go to A, we can go to D, we can go to E. Now, one thing that we try to avoid is having to go back to the parent, okay, where we are shown the parent is the parent is a child of their child node. I hope that makes sense. So what we are trying to say is because A has already been seen here, we cannot go back because we know that that is not a goal. So the children that we are going to look at are those which we haven't seen in a particular path. So in this case, we have D and we have E, like that. Okay. Then we keep expanding. We look at the children of C. We'll look at, so if we look at the children of C, the children of C will be D and G, like that. Okay, so these are some of the children that we have. So we'll keep expanding. Now, as we are expanding in this way, we formed what we call a search tree. We formed what we call a search tree. So when we form a complete search tree, we'll end up with something like this. Okay, so let me just get rid of this part quickly. Okay, so I just want to get rid of this. Okay, so a search tree will look like this, and it will show all the states that we can reach from the parent node. So now let me quickly give you some of the definitions that you will meet as we talk about searching in artificial intelligence. So the first term that you'll find is the root node. Now, the root node, we are talking about the node from which the search starts from. So the initial state or the initial node. Then the leaf node. So each of these is what we are referring to as nodes. So there is the initial node here, which is the root, the starting point. Then we have these ones at the end here, which do not have children. So these ones that do not have children are what we are referring to as the leaves or the leaf nodes. The solutions that we are looking for would typically be found on the leaf nodes. So one of these leaf nodes will most likely be the goal which we are trying to solve. So a node in a search tree having no children is what we are calling a leaf node. Then ancestor or a descendant. So an ancestor, we're talking about a parent of a node. Okay, so basically what we mean is, for example, B, the parent of B is A. So A is an ancestor of B. and then B is a descendant of A. G is a descendant of A. Why? Because as we move along the way from the parent or from the great parent, that's where we get to G. So an ancestor, when we say X is an ancestor of Y, that means X is either Y's parent or X is an ancestor of the parent of Y. So that concept of grandparent, great grandparent, that's what we're trying to say. Then there is a concept of branching factor. Okay. Now, branching factor, what we mean is from a particular node, how many possible children, the maximum possible children you can have. So here, from A, we have two children emerging from A. Even B, we have two children emerging from B. From C here, we have one child. So the branching factor, the maximum number of branches you can get from a particular node. So in this case, the branch factor in this particular search tree is 2. We can have other situations where the branch factor could be more than 2 because there are more than 2 possible states where you land from a particular node. Okay. Then a path, basically, we're talking about a complete, when we start from the start node and we end up to the leaves, so that particular sequence is what we are calling a path. Now, some paths will end up with a go node, then that is a complete path. Other paths will take us to a leaf node, but that leaf node is not a go state, and those we call them partial paths. The other definition that we have is the depth of a node. The depth of a node. So we're talking about the number of branches from a root to a node. What I mean here is this. From the root, from the root here, so this is our root, the depth, because we are starting from here, the depth is 0. Then when we move one step, okay, here, B and C are just one step from the parent, so their depth is 1. Their depth is 1. Then this DEDG, the depth here is 2. So what we're trying to say is for us to get to this level, we have to branch 2 times. So there's this one and there's this. So that is the depth that we are talking about. So that is the depth of a node. Okay, so yeah, that's the depth of a node. Then the other definition, open nodes. So open nodes, so the leaves that we have, those which haven't been expanded yet are, the nodes which haven't been expanded yet are called open nodes, or they are fringe nodes. So the nodes at the end of the tree, the leaves are open nodes. Why? Because they haven't been expanded yet. Don't worry if this concept of expansion is not clear. Yeah, very soon we'll look at an example and it will make sense. Closed nodes. We're talking about those nodes which have already been expanded, the internal nodes. So for example, here we'll say, okay, from A, I can go to B and C. Then when I move to B, I say, okay, B, I can go to D and E. C, I can go to D and G. Now, A has already been expanded. I already know where I can go from B and C. So this is a closed node. This one, however, we haven't checked whether we can, if there's elsewhere where we can go. So this is an open node, and this also is an open node. So that is the idea. So we've talked about the depth. We've talked about the branching factor. So these are the terminologies. Now, let's now look at some search algorithm, the basic concept of searching. Now, the basic concept of searching is this. First of all, what we do is we are going to keep a list. We're going to we're going to keep a list of we're going to keep the list of nodes. So initially, the list will just have the initial state. Don't worry, very soon we'll look at an example and it will make sense. The algorithm will make sense. So when you are searching, okay, when we are searching, for example, let me just copy this so that, okay, when we are searching, the first thing you do is you are going to record this, the initial state, as you're going to keep a list of states that you look at. So the first state is the initial state. That's the one you are going to look at. Then you look at the first state. Then you ask yourself, is this a go? No, it's not a go. So then what do? We record that, and then we're going to look at the children. So the list that we are compiling, is the states that we have checked. As we are moving to get to the goal, you are asking yourself, where have we been? The navigation problem, let's say Kitwe to Lusaka as our navigation problem. So we are in Kitwe. Then we say, okay, is Kitwe Lusaka? No. So we record, we have been in Kitwe. And then we now check, who are the children of Kitwe? We have Ndola, we have Chingola, we have Mufurela. We're talking about those towns that you can reach from Kitwe. So yeah, Ndola, Luansha, Chingola, Mufurela. We keep them in the list. And then we are going to decide, there has to be some strategy for deciding which one to expand next. Okay, so let's say the next town is Ndola. From Ndola, then we ask ourselves, which towns can we reach from Ndola? Those which are not yet in the list. Remember, Kitwe has already been recorded. So we've now recorded Ndola as well. So from Ndola, we can reach Kapiri, we can reach Luansha, we can reach Mufrela. We record them. Then we keep expanding just like that. So this is what the algorithm is trying to talk about. So first of all, have a list containing the initial state. If the list is not empty, then we are going to repeat the number of steps. One, get an item from the list, and then expand, check if it's a go. If it's not a go, if it is a go, return that node and the path from the initial state to the node. Else, generate all the successors of that node. And then you made them to the list. That is the loop. So don't worry about this algorithm. Let's now look at an example to make sense. Now, but before we do that, I'll come back to this at the end. Search strategies. Now, a search strategy, we are looking at how are you going to approach the search problem? How are you going to approach the search problem? Now, we can classify the search strategies into two main categories. The two main categories that we have are informed search and uninformed search. Informed search is also called heuristic search. Uninformed search is also called blind search. Now, blind search, this is a search where we don't have additional information about the domain. So, for example, when we come to the navigation problem, you and I, because we know where the different towns are, when I ask you for directions to Lusaka, I say, should I go to Chingola? Should I go to Mufrila? Should I go to Ndola so that I get to Lusaka? Because you already have information about the map of Zambia. You tell me to say, go to Ndola. From Ndola, go to Kapiri. From Kapiri, go to Kabwe. Just like that. Why? Because you have information about the domain. Now, for the agent that we are talking about, they may not have that information about the domain. In some cases, they will not have information about that domain. And if we are going to perform a search in that case, they are going to do so blindly. So that's what we are calling blind search. So they don't have any additional information about the domain. So they have to check every possible state until they find a go. That's the idea of blind search. Informed search. In informed search, the agent will have some clue. The clue could be, for example, Lusaka is south of Kitwe. So there's some knowledge about the domain. So what will happen in that case? Those states that are not in the southern part of Kitwe then will be avoided. So Chingola is taking us northwards. Chingola, Mufrila, they're taking us northwards. Then we say this will not be considered, or will only be considered at the end when the more favorable states have been explored and the solution hasn't been found. So search strategies, we're saying, can be classified into two: informed search and uninformed search. Uninformed search is also referred to as blind search. So now we are going to look at these two. Our discussion will focus on this. So for a start, we are going to talk about blind search methods, some blind search methods. And then after that, in the next session, we are going to look at informed search. So blind search, there are several methods that we have for blind search, but the common ones, the two most common methods of blind search are breadth-first and depth-first search methods. Breadth-first search, in breadth-first search, anyway, we'll discuss this, each one in its own turn. So these are the common methods that we have. So now let's look at breadth-first search. So remember the search tree. With breadth-first search, we are going to search the tree level by level. So we start with the first level. If the goal is not in the first level, we go to the second one, the third one, just like that. So let me quickly use this. So we are saying breadth-first search. With breadth-first search, we are saying we are going to search the tree level by level. So each of these is called a level. So this is level 0, level 1, level 2, level 3, level 4. So breadth-first search, when you're looking for a goal, you start here. Is this a goal? No. So now you're going to expand the children of A. When you expand the children of A, you have B and C. So with B and C, you now look at this one. Is this one a go? No. So you check the next one. Is this a go? No. So we know that B and C are not a go. So we expand the children of B and C. So then we go. So we are searching level by level from left to right. I hope that makes sense. So level by level, searching left to right, left to right. Yeah. So then we come here. Is this the go? No. We move on. Is this a go? No. Is this a go? No. Is this a go? Yes. So in breadth first search, we look at the level and the algorithm stops when it finds the go, or it has exhausted all the nodes in the in the search tree. So that's the idea. So this is a pseudocode for breadth first search. But before we do that, let's look at an example. This example, we work it out together, and then we'll come back to it. So very quickly, I'm going to now change what to share. So now I want to, sorry, just a second. I want to have a screen, a whiteboard, which I will share, and we'll try to work through it together. Okay. Okay. So I want a whiteboard. Okay. So I'm sharing a whiteboard. Yeah, okay. I'm hoping we can all see. Okay, so just a second. Um, okay, so we have this. Okay, okay. So we have this map. Now we want to look at how breadth first search is going to go about with the search. So we know the initial state is arad. So let me just mark it here. Now we check. The first thing that you have to do is you have to check. Is Harad the goal? No, we want to get to Bucharest. So what do? We now expand the children of Arad. So from Arad, let's assume we are going alphabetically to simplify our work. Uh, from Arad, where can we go? From Arad, we can go to Sibiu. We can go to Timsora. We can go to Zerind. Now we check. Is Sibiu the goal? No. We check the next one. Is Timsora the goal? No. Is Zerind the goal? No. Then we are going to expand the children of Sibiu. Now, when searching, remember, we said we avoid going back to the parent. So from Sibiu, the possible areas, towns we can go to is this one, this one, this one, and even this one. But because we've already seen Arad, we will not include. So from Sibiu, we can go to uh, this one, Ferrara. We can also go to this one, Odaria, and then we can also go to RV, this one here. We check, is any of this the go? No. So now we go to Timsora. From Timsora, there's only one child, that is this one here. Then we come to Zirind. From Zirind, Zirind also has just one child, or Daria. Okay. Then we go on, we go to Ferrara. So from Ferrara, we only have one, that is Bucharest. Okay. Then from Orient, we can go this way. But since we already know that the go will be that one, anyway, let's just expand. So from Orient, we can, so remember we started from Arad, Sibil, Orid. So we are moving from Arad, Sibil, Orid. So the only child that Orid can have is this one. Now, RV, from RV, we can go to this and this. So we can have those. We can have this one, P, or we can have this one, C. Now, in order not to confuse ourselves, once we find the goal, the algorithm stops. So I'm going to get rid of this because once we reach Bucharest, then our goal has been found. Now, how did we move, or which children did we look at? We looked at Arad. From Arad, we checked Sibil. From Sibil, we checked Timzora. From Timzora, we checked Zerint. From Zerint, we checked Ferrara. From Ferrara, we checked Odaria. From Odaria, we checked this town, this state here. From this, we also looked at this one. So from Timzora, we looked at this one. Then we also looked at Odaria. And finally, we got to Bucharest. So what you now have is your path. The path from the start, from the initial state to the goal state. So that is our path. So now, one thing that I just need to mention here, I know we're going to have a concern to say, how come some states are appearing more than one time? This is going to happen. Why? Because these are children originating from different parents. For example, the first O here is this one. Now, this one is coming from Sibil. So we move from Arad to Sibil, then to Odario. This other O, we started from Arad, went to Zerint, then Odario. So it's like we're saying you can get to this point using different routes. Going to Lusaka. When you want to go to Lusaka, you can go from Kitwe, Ndola, Kapiri, all the way you get to Lusaka. You can also go to Kitwe, Luansha, Mpongwe, Kapiri, you're moving. You can also go from Kitwe, Mufurira, go through Congo, come out through Pika there, Serenge, until you get back to Lusaka. There are all those. So the key, the child that, for this to be listed as a child, we shouldn't have, we avoid repetitions. So remember, what we said was when you move from Arad to Sibil, you can't go back to Arad because that is going to form a loop. So as long as we avoid a loop, then we are good to go. So that is that is about breadth-first search. That is an example of breadth search. We're going to look at more examples. So now, let's now go back to our presentation. So just a second. Okay, so now let me share my presentation. So having shared my presentation, okay, sorry. Okay, so having shared my presentation, I'll now, so like this is a concept which we were talking about, how we are going to expand the children until we get to the goal. Now, let's now talk about the pseudocode, having understood how to do breadth first search. So sorry about that. So the first step in this algorithm was create a list, and for the list, the first item you should have is the start state, the initial state. Now, when you have this list, as long as it's not empty, get the first element of Q. If it is a go, you report success and you quit. If not, you are now going to get the children of Q1 and you remove all the children which represents loops. And you get the children, put them at the back of Q, and you continue until you get to the end. What we mean here is this. We look at Arad. Is Arad the goal? No. So now we look at the children of Arad. We put them in the list. We put them in the list, but their priority, if there was a sibling of Arad, consider the sibling before you consider the children of Arad. So like here, when we find that Arad is not a goal, then we have Sibyl, Timsora, Zerint. You check Sibyl. Is Sibyl a go? No. We expand the children. We get the children of Sibyl. After getting the children of Sibyl, what we now do is for the children of Sibyl, we will not consider the children of Sibyl before we consider the siblings of Sibyl. The sibling of Sibyl are Timsora. So first finish this level and then go to their children. I hope that makes sense. So that is breadth first search. Okay, so let me stop here for this video. In the next video, we are now going to look at depth first search and then have a discussion where we compare these two. So thank you very much for listening. See you in the next video.